This is the ISD 555 interim presentation for Team 14, presented by Arbaz, Eddie, Caitlin, Tyler, Esme, and Yue. At a high level, our system, the intercity train system, seeks to minimize the cost associated with downtime, operating costs, and passenger wait times. This is done through three subsystems. First, the mechanical efficiency defines the physical design of the train, which impacts the operating costs from the energy consumption perspective. Thus, it seeks to minimize the energy consumed by the train and therefore costs associated with that. The demand planning subsystem defines the locations and frequency at which the train stops as a function of the input demand. Thus, its objective is to minimize the cost of any unmet demand. The maintenance planning subsystem is our final subsystem, and it's concerned with the cost of maintaining the trains from the operating and also from the downtime perspectives. Thus, its objective is to minimize maintenance costs. These three subsystems work together through shared variables like number of cars, energy consumption, and train availability to synthesize an optimal solution.
First subsystem of our design optimization problem is mechanical efficiency of train. We define parameter, variable, constraints, and objective function. We have a common input which is total distance across all subsystem and another number of cars needed from another subsidiary system. Here we define constraints setting total train length and motor efficiency, including site constraints on size and safe speed. Our main objective is to minimize power consumed by the train. We have considered assumptions for simplification of our problem, such as the constant mass of car frame for all car sizes, along with constant environmental and material properties. Here we define number of passengers, their average mass, and space they occupy, all contributing to the total resistance force driven by the train.
We use the fmincon solver in MATLAB to optimize our subsystem, which handles linear and nonlinear constraints and is effective in locating a local minimum if a good initial guess is made. 5 optimization trials were run, with each trial conducted with different initial value or design parameters to explore the behavior of the solver. From the optimization runs, we were able to see that changing the initial value did not have any effect on the outcome of our subsystem, showing that our local minimum is indeed the optimized point. Also, for all the runs, the dimension of the train cab was at the lower boundary of the side constraints, which aligns with the expectation that the smaller the cab, the more efficient the train is physically. The average speed of the train is well optimized by balancing the aerodynamic drag and the motor speed to minimize the total energy consumed.
The second subsystem of our intercity train system is the demand planning subsystem. We began by setting up our optimization model defining parameters, design variables, constraints, intermediate variables, and the objective function, which was to minimize the cost of unmet demand, which is equal to the number of individuals who couldn't travel times the cost that they would have spent traveling. Of note, our train availability parameter is an input from our maintenance planning subsystem, and our demand function is a decaying exponential function that depends both upon the time of day and the distance an individual is from the city center. When talking trade-offs with constraints and our objective, we want to minimize the number of stops because that would minimize the time it takes to run the route, and therefore we would have a need for less trains. But we also want to maximize the number of stops because that allows us to get more people on the trains to meet increased demand. After developing the framework for our model, we had to develop an approach to solve it. We started by identifying places where demand would not be met, such as unmet stops, not having enough trains, or trains being full. We decided to use simulation to study this subsystem because of the ability to rapidly implement different scenarios and see the results real time. We did make some assumptions regarding our model, which allowed us to bound it to make it simpler to solve within the context of this problem. We did follow major modeling steps that were outlined within the course, which also involved taking the constraints and writing them in the negative null form so that we could then input them to our genetic algorithm code and execute it until we converged on the solution. We decided to use MATLAB for this due to its processing capabilities and built-in optimization functions, one of which was the genetic algorithm function, which allowed us to define integers for constraints of bounds, was useful for locating global minimum, and can be used to solve both linear and nonlinear constraints.
To assess the change in cost of unmet demand, we varied the number of trains available. This was chosen as it will be an input to our subsystem from maintenance planning. The optimization was broken up between low and high demand for each input and summed to a total cost. From the analysis, we found that for less trains available, the time between departures is longer as there aren't enough trains to space them apart less, driving up cost of unmet demand. For more trains available, we also found that cost began to increase. Since we assume all trains available are used, it resulted in an increased wait time and therefore less met demand.
The next subsystem is subsystem 3, which focuses on maintenance planning. The objective function is to minimize the train maintenance cost. We have on the slide outlined the parameters and the design variables, of which we have energy consumption cost, which is taken from subsystem 1. The constraints, which are the maximum number of trains under maintenance, is lower than the capacity in the harbor. The maximum working hours per employee per month is less than 160, and the maximum number of shifts needed per train maintenance is less than 1. This is to ensure that employees don't have any opportunity for overtime, to minimize costs, and to ensure that they have adequate rest between shifts to minimize accidents. And we want to constrain the amount of time required for a shift to conduct maintenance to simplify the problem set.
After defining maintenance planning subsystem optimization framework, we set up a few assumptions like there's only one harbor, each train needs to be maintained 3 times a month, etc. to complete the mathematical modeling. We decided to use MATLAB fmincon function to perform the optimization since it can deal with both linear and nonlinear constraints. Number of cars per train and the electricity cost are 2 design variables from the other subsystems. Since we haven't started to work on the interactions between subsystems, we set these 2 design variables as a fixed value for our maintenance subsystem optimization for now. In the first 4 runs, we started with different initial conditions and it led to the same optimum finally. The lowest monthly maintenance cost can be achieved by having 40 maintenance technicians and setting the harbor capacity to be able to service 3 trains in the same time. When there are 7 cars per train and the electricity cost is set to be $23.5 per 50 kilometer. In the last round, we started with a random larger number of technicians on purpose, and it led to a higher monthly maintenance cost for comparison.
Thanks for tuning in to our interim presentation.